Here we go, video number 5. Hopefully this will be the last one, we'll see. Okay, so we just talked about why larvae would evolve to find such low chance of survival and such low chance of finding suitable substrate. And the idea was that some offspring will find and occupy suitable habitat, even if the parent's patch becomes unsuitable. So it's spreading the risk out, so that if something happens, you've got so many babies that are just bursting apart enough that at least some of them will find the right place to live, even if some disturbance completely destroys where the parents live. So how would you test this? So this guy did this really cool experiment looking at Cretaceous gastropods, fossils, on these 3 outcrops on the east coast in Texas. And apparently, looking at gastropods, you can tell if they're planktotrophic or leucotrophic because of the way that larval shell is formed, and that tip of the larvae of the shell continues even when the shell is full grown, and you can see that in the fossils. So he was able to determine how long these species were on average in the fossil record, and therefore their geologic duration, which is what we're looking at here, and what their geographic range was. So here we have planktotrophic larvae, and down here we have non-planktotrophic larvae, so probably mostly leucotrophic larvae. So remember, planktotrophic larvae have a much larger pelagic larval duration, PLD, so they disperse a lot farther, whereas the leucotrophic species have just a few days, maybe, of pelagic larval duration, so they don't disperse nearly as far. Okay, so how much are planktotrophs really in the geologic record much longer than non-planktotrophic larvae? Definitely. So the average duration in the geologic record for planktotrophic gastropods is 6 million years. For non-planktotrophic species, it's 2 million years. So they last 3 times as long in the geological record. So that means they're getting lower extinction rates. Planktotrophic species that have long pelagic larval duration have lower extinction rates than non-planktotrophic larvae. And then if you look over here at these graphs, this is about the geographic distribution of these fossils, of these different gastropods. So the mean in geographic distribution in kilometers for planktotrophic species is almost 2,000 kilometers. The mean geographic distribution for non-planktotrophic species is 380 kilometers. So planktotrophic species have 5 times the geographic range of non-planktotrophic species. So species that can disperse really far, lower extinction rates, and have a much larger geographic range. So that's some definite evolutionary advantage. That's pretty good reason to try dispersing really far and have lots of babies. Works for me. Okay, so now we'll go on to where I was really hoping to start this lecture, which is, since we have talked about reproduction and planktonic larvae, we'll move on to settlement and maybe even post-settlement processes in this lecture. So for settlement, once the larvae get back into the area where there's hopefully some suitable habitat, maybe back to the coast, they have to find that suitable habitat, choose the right place where they want to settle, they have to actually settle, and then they have to metamorphose, so they no longer look like a larvae, they look more like a juvenile, or a mini version of the adult. So remember, we talked about what the differences are between settlement and recruitment in that first discussion paper we read the first week, Keogh and Downs, 1982, I think. So remember, settlement is when the individual is transitioning permanently from the pelagic environment, from being larvae, to the benthic environment. So it's transitioning from the planktonic dispersive stage to the sessile, meaning not moving at all, or sedentary, not moving much, benthic stage. Recruitment, on the other hand, is theoretically the same thing, but what it really means is it's the addition of individuals to the population. So theoretically, that would be the same. But the problem is the individual cell is really, really little. It's hard to see them in the field. It happens fast, it's unpredictable, they're really small, often occurs at night, so we are not going to see individuals as soon as they settle. It's just not going to happen. So really what it means is it's when we first see the individual. It's when they're big enough for us to catch them, for us to observe them. The first time, we go out to the site to see them. So that's really not the same thing. So remember we read this paper, Kieg and Downs, the first week of class, and they said in their introduction it's important to distinguish between settlement and recruitment. Because if you see a non-random pattern of recruitment, it could be because the organisms are actually settling differently, or it could just be that they're getting mortality between when they settle and when we observe them. It's really important to focus on settlement. So this paper looked at the post-settlement processes affecting polychaetes and bryozoans. And some of the species were preyed very heavily upon by fish right after settlement, and it really did modify their recruitment patterns. And so these predation events were occurring within about 3 weeks of the settlement. So if they had just been looking for recruits within every month or two, they would have seen a completely different pattern. It would have been a very misleading pattern. So their argument is you really have to focus on settlement, and you have to recognize that settlement and recruitment are two completely different things. So Kieg and Downs argue that recruitment is very subjective. It really depends when you're looking, what you're measuring. And recruitment includes both settlement and early post-settlement mortality and movement. Some individuals can move after they first settle, like mussels, for instance, that Kristen and told us about. So how you estimate recruitment and how it's related to the actual settlement depends on how often you're sampling and what those patterns of post-settlement mortality look like, whether they're density independent or density dependent. So basically the key message here is settlement is not the same thing as recruitment. You need to know what they both are, and you need to know what the differences are. Pretty key for marine ecologists. Okay, so here's just a quick model. If you graph time on the x-axis and number of individuals of the species, or generally the cohort, on the y-axis, there's settlement at time 0, and the two different locations, there's a mortality rate of 0.4 or 40% mortality rate of 0.6 in every time period. You get this different pattern. So if you were able to settle, if you were able to measure recruitment right at the time of settlement, you would see 100 individuals in both locations. But if you settle one time period later, you'd see, 80 or so at the one site and, 45 or 50 at the other site. And the later in time you go, the more differences you're going to see. So if you want to get a really good relationship between settlement and recruitment, you have to sample as often as you possibly can. And then you're going to start catching the actual settlement. So if that rate of mortality varied among the sites, that would be what's contributing to the pattern, as well as any actual settlement patterns. The rate of mortality would be completely distorting the settlement, what you think you're seeing are settlement patterns. So it would, like I said, it would completely mess with your conclusions about settlement. So you really have to check early and often. Okay, so we've been going through this, and now we're going to look at post-settlement processes. So, down here, early post-settlement mortality and juvenile development, a little bit. So everything that happens to adults can also happen to planktonic larvae and new settlers, which is what we usually call recruits. There can be intraspecific competition, there can be interspecific competition, there can be predation, there can be disturbance, there can be physiological stress, all kinds of things. And because you get that intraspecific competition, and most species have a more or less carrying capacity, and they show logistic growth, the density at time t influences the population growth to time t plus 1 if you have density dependent growth. So the number of, say, adults that you have at time t is going to influence how that larvae are doing at time t plus 1. So you have interaction between different life stages. They influence each other's performance and also the next generation. So if you think about something with a simple life history like cats or dogs or people, By the way, here's my favorite dog, Hula. She has learned a new trick recently to drink out of the bird bath. Adults reproduce, have juveniles survive, grow, mature, and become adults. It's pretty tightly linked. The adults and juveniles are probably living in more or less the same place. Not too much dispersal for cats or dogs. Okay, a little bit more now for people than there used to be, say 100 years ago. But they're pretty tightly linked. It's all in the same place. So because of limited dispersal, its reproduction, survival, growth, maturity all happens in more or less the same local environment. So the adults and juveniles are interacting directly and influence each other's performance as well as the next generation. However, when you look at our complex life history of fishes and invertebrates that have this planktonic larval stage, if the settlers are coming from somewhere else, then the local supply of larvae is not the same thing as local reproduction. The local supply of larvae is not coming from the adults. So you have this decoupling, which can potentially destabilize the population. So we're going to talk about this more later. So in our simple life history, remember when we talked about exponential growth and logistic growth, we talked about how birth rate helps regulate the population, that when there's, a lot of adults, the birth rate declines. Well, we're not really looking at birth rate anymore. Now we're looking at settlement rate. So it's the settlement rate that regulates the population in species with a large larval stage. So just how much population is open has a lot of effects on what's going on in that population and in the larger mammal population. So that's what we're going to talk about at the next lecture on Monday, is how does the openness of a population impact its structure, stability, and diversity. So I hope this worked out for you. Make sure you do the quiz by midnight Saturday. Thanks. Bye.